And welcome back. As we continue our cosmic journey, let's go ahead and focus back on home a little bit here and talk about Earth just for a few lessons, particularly by starting at a kind of global perspective at our own home planet. Now, you might have referred to or heard the Earth referred to as the blue marble. Now, we call this because of primarily the water that's here, but we have to understand that Earth is a medium-sized planet. It's composed primarily of heavy elements such as iron, silicon, and oxygen. Now, Earth's orbit, as we know, is nearly circular. It's actually an elliptical orbit, but it's nearly circular in that elliptical fashion, and Earth is actually warm enough to support liquid water on its surface. In fact, it's one of the few planets that can do so. And it's the only known planet in our solar system that is in the habitable zone, which is one of those zones that is capable of having life, that actually led to the development of life as we know it. So let's look at a few properties of Earth here, just to kind of reinforce what some of the cool things about our planet. Our semi-major axis is 1.00 AU, or astronomical units. Our period, so the time it takes for us to traverse around our orbit, is 1 year. Our mass is 5.98 times 10 to the 24th kilograms. We have a diameter of 12,756 kilometers. The radius, of course, is half that at 6,378 kilometers. Our escape velocity, which is what you need to escape the pull of Earth's gravity, is 11.2 kilometers a second. We have a rotational period, so that's how long it takes to make one day, is 23 hours, 56 minutes, and 4 seconds. We have a surface area of 5.1 times 10 to the 8th kilometers squared, and we have a density of 5.514 grams per centimeter cubed, and atmospheric pressure of 1 bar. So, with that out of the way, let's actually go ahead and dive into the actual nuts and bolts of what makes our planet the way it is, by first looking at the interior. So the interior of a planet is difficult to study, because obviously we can't just simply open up the planet and say, oh, well, this is what's in here. And its composition and structure, instead, we have to determine this through indirect means. Our only direct experience with our planet is the outermost skin of Earth's crust, a layer no more than just a few kilometers deep. Now, Earth is composed largely of metal and silicate rock. Now, most of this material, of course, is in a solid state, but some of it is hot enough to be molten. Now, the structure of material in Earth's interior has been probed in considerable detail by measuring the transmission of seismic waves through Earth. These are waves that actually spread through the interior of Earth from things such as earthquakes or explosion sites. So let's talk about those seismic waves just for a second, because they're very important in understanding what actually is able to be learned from Earth's interior. Seismic waves travel through a planet just like sound waves travel through a medium. Just as sound frequencies vary based upon the material that you're trying to put sound through, so does the planet's response on its composition and structure. By monitoring the seismic waves at different locations, scientists can actually learn about the layers through which the waves have traveled. Now, some of these vibrations travel along the surface, others pass directly through the interior. Seismic studies have shown that the Earth's interior consists of several distinct layers with different compositions. Now, as these waves travel through Earth's interior, the waves will either bend or refract, so that some seismic stations on Earth receive the waves and others are in kind of these more shallow regions. Now, detecting the waves in a network of seismographs helps scientists actually construct a model of what we believe Earth's interior is, showing both liquid and solid layers. So, let's start off by looking at the Earth's crust, which is the easiest layer for us to observe. The top layer of Earth is, of course, referred to as the crust. Oceanic crust covers about 55% of Earth's surface and lies mostly submerged beneath the oceans. It's typically composed of volcanic rocks called basalt, which are primarily composed of the elements silicon, oxygen, iron, aluminum, and magnesium. Now, the continental crust, which is, of course, our land masses, covers about 45% of the surface, some of which is actually also beneath the oceans. Now, the continental crust is thicker and is composed predominantly of granite. If we go a little deeper, we can move to our next layer, which is the mantle. Now, the largest part of our solid Earth is referred to as the mantle, and it stretches from the base of the crust downward to a depth of about 2,900 kilometers. The mantle is mostly solid, but at the temperatures and pressures that are found here in the mantle, a mantle rock can deform and flow kind of slowly. Now, the density of the mantle increases downward from the compression produced by the weight of overlying material. Now, samples of upper mantle material are occasionally ejected from volcanoes, giving us a kind of detailed analysis of its chemistry. If we want to go deeper still, of course, we can go directly down to Earth's core. Beginning at a depth of 2,900 kilometers, we encounter the dense metallic core of Earth. With a diameter of about 7,000 kilometers, our core is substantially larger than the entire planet of Mercury. Now, the outer core is liquid, but the innermost part of the core, which is about 2,400 kilometers in diameter, is probably solid, due from the intense heat and pressures. Now, in addition to iron, the core probably also contains substantial quantities of nickel and sulfur, all compressed to a very high density. Remember, it's got all this overlying material on top of it that's just pushing down on all sides. Recall that this layers that we've seen here, so the crust, the mantle, the core, this differentiation is what separated the Earth into its layers, allowing heavier elements such as iron to sink to the center of the Earth. Now, that of course, having that iron core lets us very easily have things like a magnetic field and a magnetosphere. If we find clues about Earth's interior from its magnetic field, we can see it as if a giant bar magnet were inside of the Earth, aligned approximately with the rotational poles of the Earth. This magnetic field is generated by the moving material within Earth's liquid metallic core that creates a circulating electric current. When you have many charged particles moving together like that, they actually produce a magnetic field. Now, Earth's magnetic field extends into the surrounding space around our planet, where it can actually trap small quantities of electrons and other atomic particles. This region, we refer to as the magnetosphere, is where Earth's magnetic field dominates over the weaker interplanetary magnetic field that actually extends outward from the Sun. So even though the Sun is larger, because of our distance and proximity, we can actually kind of manipulate the space even though the Sun is there. So if we look at Earth's magnetic sphere, it actually is a very important thing for us to have here in our region around our planet. The charged particles trapped within our magnetic sphere come from the hot surface of the Sun on the solar wind. Solar wind provides particles and stretches our field in the direction pointing away from the Sun. Now, Earth's magnetic sphere extends about 60,000 kilometers in the direction of the Sun. In the direction away from the Sun, though, the magnetic field can carry as far as the orbit of the Moon or even beyond. Now, the regions of high-energy ions in the magnetic sphere are often referred to as the Van Allen belts, as you can see here in this diagram.